Today we are going to talk about complements of numbers. As I said, we are living in digital worlds, digital TV, digital camera, digital computers. So complements are used in digital computers to simplify the subtraction operation. And simplifying operations lead to simpler, less expensive circuit to implement the operations. There are two types of complements, okay? For each numbering system, for each base R numbering system, okay? So one is going to call R's complement, and the second one is going to be R minus 1's complement. For example, for base 2, which is binary, is going to have 2's complement and 1's complement. For decimal numbers, which is base 10, you're going to have 10's complement and 9's complement. Okay. For, let's say you have a number n in base R, which this number is going to have n digits. So how we can compute R minus 1's complement? Of this number n. So the equation is going to be R to the power of n which is number of digits, minus 1, and then minus your n, which is your number. Okay. For example, if you have a decimal number, this is base 10, and you want to compute R minus 1's complement, which is, since this is a base 10, you're going to have 9's complement. It's called 9's complement. So how you compute it, you're going to say, okay, R here is R is 10. So you're going to have, using this equation, you have 10 to the power of the digit, which is 6. So 10 to the power of 6 minus 1, and then minus your number. So you just use this subtraction, you get your ninth complement. So this is for base 10, finding R minus 1's complement. Let's see how we compute 1's complement and 2's complement for binary number. So for binary numbers, so in binary R, basically your base is going to be 2, yeah? So you're gonna have R minus 1's complement, which is called 1's complement. And you also have R's complement, which is, since this is R is 2, it's called 2's complement. As you know, in binary number, the digit is only going to be 1 and zeros. So for 1's complement, you just changing 1's to 0 to zeros and zeros to 1. Just flip each of these digit in a binary number. For example, if you have 0, 0, 1, 1, the ones complement is going to be just 1, 1, 0, 0. That's it. You just flip the bit. So it's going to give you ones complement. For the twos complement, there are two methods to find the twos complement. One, leaving all least significant zeros and the first one unchanged. Until you get the first one, you don't change it. Then after that, you're gonna and replacing ones to zeros and zeros to ones in all other higher significant bits. Okay, so let's say you have 1, 1, 0, 1, 1, 0, 0. Okay, so this is the least significant bit, LSB. So you start from the right. You keep all the zeros unchanged until you get the first one. Means these 3 bits is going to be unchanged. So 0, 0, 1 unchanged, and then you flip the rest. So you're going to get 0, 1, 0, 0. So this is going to be the two's complement. The second method to compute the two's complement is much easier. You just find the ones complement finding ones complement and then you add it by 1. That's it. So let's look at our example again. 1, 1, 0, 1, 0, 0. So you just find the ones complement. So ones complement is easy. You just flip the bits. 1, 1, 0, 1, 0, 0. And then you add 1. Okay, this is a summation in binary. So for binary, if you have 0 plus 0, you just get 0. 0 plus 1, you get 1. 1 plus 0, you get 1. But for for 1 plus 1, 1 plus 1 is 2 in decimal. 2 in decimal, which is base 10, in binary is going to be 1, 0 in binary. So you get 0, and then 1 is going to be the carry. So remember, 1 plus 1 in binary is 0. So here you get 0, answer of this summation, and then 1 goes to carry, you get 0, and then 1, 1, 0, 1, 0, 0. So if you compare this with the result we computed in the first method, you can see that we get the same answer. Okay, that's it. So this is two's complement for binary numbers. Okay. Okay, let's say you have two numbers m and n, and each of these two numbers have n digits. So you have m and n. Okay, so you want to subtract m from n. Okay, so the step 1 in the subtraction of m minus n, finding m minus n, is first you add So you add m to the r's complement, and it depends on the base of the number. These are base r, okay? M and n, we consider that these are base r, okay? So first you add m to r's complement of n. So the equation for this operation is going to have m plus, and then you're going to have r's complement of n, which is have this equation. That's the r's complement of n. So you can just write it m minus n plus rn. Okay. Then in a step 2, it depends on the numbers. If m is less than n, then the sum of on the step 1 does not produce an end carry. Okay, so let's say you have m is 72,532. Your m is this one, and now we are talking about when m is smaller than n. Okay, so n is going to be, let's say, 3,250. Okay, so we want to subtract m minus n. Okay, so in this case, remember that the number of digits for these two numbers needs to be the same. So for m, it has 5 digits. For n, it has 4 digits. So we're going to add 0 at the end of number n to get 5 digits. Okay, 5 digits. So you have to make it the same number of digits. Oh, sorry, we wanted to consider, okay, let's just switch this. We wanted to consider the case that m is, for the case that m is less than n. So you want to do this subtraction instead of using a normal way that you do the subtraction. You want to do the complement, use the complement approach. Okay, so as I said, you just need to add your m. This is your m. You add m to r's complement of n. Okay, so instead of writing n here, you want to do the addition. Okay, you want to do the addition here, but here you need to put r's complement of n, which, since this is decimal, is going to be tens complement of n. First find the tens complement of n. So this is the tens complement of n. So you just replace it here, you get, and then you do the addition. Okay, you get 81703. So since this one doesn't have any carry, what we do to get the answer, you just find the tens complement. So the answer of m minus n is going to be minus tens complement of the sum, which your sum is here. So m minus n is going to be minus, and then you find the tens complement of the 30718. So it's going to be 69 to 82. So that's going to be the answer for m minus n. So to summarize, the first step, you just add m to r's complement of n. And then if the answer doesn't produce any n carry, then m minus n is going to be minus the tens complement of sum. So for the another case, which is m greater or equal to n, in this case the sum will produce carry. Sum will produce an end carry. In this case, you just discard the end carry, and what is left is going to be the result of m minus n. Let's look at the example again. So here we're gonna consider the same number. M is 72, 532, and n is going to be 3250. So as I said, since it has one less digit, you just add 0 for n. So the first step, just m plus, you just add m to r's complement, which is tens complement of n. Tens complement of n, so which is 96, 750. You just add these two. So this is your sum. You can see now you have carry. Okay, you can discard the carry, and the answer is going to be this. So you just discard the carry and you get the answer. To discard the carry, you just you can consider the subtraction of 10 to the power of 10 to the power of 5. 5 is the number of digit. You just discard the carry and you get the answer. Okay, so that's the case when m is greater or equal to n. So these are in decimal words. Okay, we are basically more interested in binary number because we're gonna have digits, bits in logic circuits. We're gonna have binary numbers. So let's look at the binary number now. Let's say you have two binary numbers. One is x is 1010100, and then you have your y, which is 10000 and 11. First, we want to find x minus y. Okay, as I said, you just write down x. You just write down your x, 1010100, and then you have to find 2's complement of y. 2's complement of y. 2's complement of y is just easy. You find the 1's complement plus 1. So 1's complement is just switching the bits. 0 0 1 1 1 1 and then 0. And then you add 1. So you get 1 0 1 1 1 1 0. So that's the 2's complement of y. So you just add it now to this. You get 1 0 1 1 1 1 and then 0. So the answer is 1 0 0 0, and then you get 0 again, and then you get 0. Okay, 1000, and then you have one carry at the end. So this is the end carry. So it's produced the end carry.
You just discard the end carry and you get the answer for x minus y.
Okay, so that's for part A, which we wanted to compute x minus y. Let's see what we get for y minus x. So let me write it down again. Y is 1 0 0 0 0 1 1, and your x was 1 0 1 0 1 0 0. So now we want to find y minus x. So you write down y, you just write down your y, and then you're gonna have 2's complement of your x, which is going to be, the 2's complement is going to be 0. So you're gonna have the 1's complement plus 1. Okay, let me write it down. The 1's complement is just 1 1 0 1 0 1 1 0 1 0 1 0, and then you added 1 to this number, the 1's complement. So 1 1 is going to be 2, so you get 0, and then another 1 goes to top, so that it's carry. So 1 plus 1 again, it's 2, you get 0, 1 goes there, 1 plus 0, you get 1 1 0 1 0. So 0 0 1 1 0 1 0. So you add these, two number, you get 1 1 1 1 0 1 and 1. So there is no carry, there is no end carry. What you get for answer is y minus x is minus the 2's complement of the sum. So you get minus 0 0 1 0 0 0 1.
Now let's talk about signed binary numbers.
So in binary numbers, the sign is going to be represented by the left most significant bit. Okay, so the sign represented by the left most position of the binary number. If you have signed binary number, the leftmost bit is going to be your sign number, and then the rest of the bits is going to represent your number. But if it's unsigned, so this is for sign, so this is going to be your number, this is going to be the sign. But if it's unsigned number, unsigned binary number, then all the bits is going to represent your number. So all of them is going to be represent your number. Let me give you an example. For example, if you have 0, 1, 0, 0, 1. So in unsigned binary, what's this number in decimal? So this is going to be 9. But if it's signed number, then in this case, let me write it again. In the signed binary, then the left most bit is going to be represent your sign. If it's 0, it's positive. And if it's 1, it's going to give you negative number. And then the rest of the number is going to give you your number, so which is, again, it's 9. So it's going to be plus 9. Okay. Now, if you have this number, 1, 1, 0, 0, 1. In the case of unsigned, what's the number in decimal? What's the number? 25. Yes. 2 to the power of 3 plus 2 to the power of 4 plus 2 to the power of 0. You get 25. So you get 25. But if it's signed number, then you just consider 1, 1, 0, 0, 1. The 1 is going to be your sign, which is negative, and then the rest is going to be your number, which is 9. So it gives you minus 9. Okay, so for a signed binary, the bit, the leftmost bit represent the sign, and the rest of the bits represent the number. Okay, so this approach is called signed magnitude representation. So it's obvious. So you have sign, and then you have the magnitude of your number. So signed magnitude representation. You also have another approach which is called signed complement representation. In this case, for example, positive 9, it's going to give you, let's say you have 8-digit number, 8-bit number, so 1001. A negative number is indicated by its complement. So the representation of minus 9, so as I show it in the sign magnitude, you can write it as 1001 is your 9, and then you get 0001. So this is an 8-bit. The previous example, it was 5. So this is 8-bit. So this is your sign bit. Okay. So it gives you minus 9 in the sign magnitude. In the sign ones complement, just get 1 1 1 1 0 1 1 0. So that's minus 9 in sign 1 complement. In the sign 2's complement, you're going to get 1 1 1 1 0 1 1 1. You just add 1. So that's the sign 2's complement. So as I mentioned before, we said that the computers are working with binary systems, but people are mostly more comfortable with decimal numbers. So that's why there are different coding techniques that convert the decimal to binary. One of the most famous one is BCD. So it's a binary coded decimal code. So in BCD, you're gonna have decimal numbers 0 to 9. And then you have your BCD digits. So this is a 4-bit code. So you're gonna have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1. And 1, 0, 0, 1. So you get until 9, and from 9 to 15, we don't consider that there is no meaning in BCD. So from 1, 0, 1, 0 through 1, 1, 1, 1, the rest is going to have no meaning in BCD. So there is another code which is very so famous, is Gray code. The Gray code is can be have I can show it in this table. So the Gray code is going to be 0, 0, 0. So this is the decimal. Decimal is going to be 0 to 15. And then you have your Gray code. So the difference is in binary, in BCD. In BCD, we say 0, 0, 1, 0 represent 2 in decimal. But in Gray code, you have 0, 0, 1, 1 is going to represent 2. Okay? I'm going to explain you why. So 0, 0, 1, 0 is going to be 3. Then you have 0, 1, 1, 0 as your 4, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1 is going to represent 10. And then 11 is 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0 is 15. Okay, so this is a Gray code to decimal. So the why we choose, for example, the 2 is going to be 1, 1 instead of 1, 0. So the reason is that in Gray code, we want to the neighboring numbers only have difference only in 1 bit. Like the 1 and the 2, we're going to have only 1 bit difference between these two. Okay, and then again with the neighboring of 2 and 3, we only have difference in 1 bit. If we choose 0, 0, 1, 0 and then 0, 0, sorry, the upper neighboring. So 0, 001. The difference between these two neighbor number, is going to be 2 bits. Okay, so that's when you're transmitting, let's say you're messaging, typing a message, and it's going to convert it to binary, zero and ones, and then it's going to go over the air, and then at the receiver side you're going to get the message and recover the message. Okay, in this case, since you have 2 bits different, then the two neighboring bits different, then you're gonna get more error. Okay, the percentage, or the chance of getting errors when the neighboring bits have more than 1 bits difference, is going to give you more errors. That's why they use gray code in transmission in mobile communication as well. So they choose this code since each of the neighboring numbers, they have the difference only in 1 bit. Okay, that's it for today. So we covered the complement, the signed binary number, and some of the coding system between the binary and decimal.